In the sweltering heat of the South Pacific, American pilots faced a terrifying reality. Japanese Zeros could outmaneuver them in nearly every dimension of aerial combat. But in 1943, one mechanic's seemingly absurd modification, inserting thin metal shims into engine mounts, transformed the P-38 Lightning from a struggling interceptor into a vertical climbing monster that left Zeros gasping for altitude. What the enemy dismissed as impossible would become their undoing, and the story of how a crazy field modification defied engineering orthodoxy reveals the hidden war fought not with bullets, but with thousandths of an inch. New Guinea, March 1943. The 5th Air Force faced an enemy that owned the sky. The P-38 Lightning arrived in the Pacific theater with a reputation forged in European skies. Twin-engine power, heavy armament, and a distinctive twin-boom design that promised air superiority. But within weeks of combat operations over New Guinea and the Solomon Islands, American pilots discovered a horrifying truth. In vertical climbs above 15,000 feet, the vaunted Lightning became a death trap. Lieutenant Colonel Thomas Lynch, commanding the 39th Fighter Squadron, documented the crisis in a classified report dated March 18, 1943. Enemy Zeros consistently outclimb our P-38s in vertical engagements above 15,000 feet by margins of 800 to 200 feet per minute. This performance deficit has resulted in 23 confirmed losses in the past 6 weeks, with pilots unable to execute escape maneuvers that require sustained vertical climb capability. The strategic implications were catastrophic. The entire Allied air campaign in the Southwest Pacific depended on establishing air superiority over Japanese-held territories. Yet the Zero, lighter, more agile and powered by the Nakajima Sakai engine, could simply climb away from pursuing Lightnings, then dive back down with energy advantage for devastating attacks. American bomber formations suffered mounting losses as their fighter escorts proved unable to intercept high-altitude Zero attacks. The numbers told a grim story. Between January and March 1943, the 5th Air Force recorded 847 combat engagements with Japanese fighters. In 312 of these encounters, 37%, American pilots reported being unable to maintain pursuit in vertical climbs, resulting in broken contact and missed opportunities. More critically, 89 P-38s were lost when Zeros exploited superior climb rates to gain positional advantage, then executed slashing attacks from above. The problem defied conventional understanding. On paper, the Lightning's twin Allison V1710 engines, producing 1,125 horsepower each, should have provided overwhelming power. The aircraft's total thrust exceeded the Zeros by nearly 1,800 horsepower. Yet in the thin air above 15,000 feet, during sustained vertical climbs, the Japanese fighter consistently pulled away. Major General George Kenney, commanding the 5th Air Force, faced a strategic dilemma that threatened the entire New Guinea campaign. His intelligence officers had intercepted Japanese communications, revealing that Zero pilots had developed specific tactics to exploit the Lightning's vertical climb weakness. The Japanese called it Taka Nobori, the Hawk's Ascent, a maneuver where Zeros would bait Lightnings into vertical pursuits, then climb away while radioing positions to other fighters for coordinated attacks. In Washington, the Army Air Force's Technical Division at Wright Field received urgent requests for solutions. Engineers pored over performance data, examining everything from propeller pitch settings to supercharger boost pressures. They recommended modifications to intercooler systems, adjustments to fuel mixture ratios, and revised combat procedures. Field mechanics implemented these changes with meticulous precision. Nothing worked. The Lightning continued to hemorrhage energy in vertical climbs, its twin engines roaring at full power while the aircraft seemed to hang in the air, losing momentum as Zeros climbed effortlessly above. Pilots reported a phenomenon they called the wall, a point around 18,000 feet where the Lightning's climb rate would suddenly collapse, as if the aircraft had hit an invisible barrier. Enter Staff Sergeant Raymond Ray Tolliver, a 34-year-old engine mechanic with the 475th Fighter Group's maintenance section at Dobodura Airfield. Tolliver had spent 15 years before the war working in automotive racing, specializing in high-performance engine tuning for Indianapolis 500 competitors. His expertise lay not in theoretical aerodynamics, but in the practical, hands-on understanding of how engines translated power into motion. Tolliver noticed something the engineers had missed. During post-flight inspections of Lightnings that had engaged in vertical climbs, he observed unusual wear patterns on engine mount bolts and slight deformations in the mounting brackets. The pattern was consistent. The upper engine mounts showed compression stress, while lower mounts exhibited tension indicators. On April 3, 1943, Tolliver made a request that his commanding officer initially dismissed as absurd. He wanted permission to deliberately misalign a Lightning's engines by inserting thin metal shims, precision-cut pieces of aluminum ranging from 0.015 to 0.045 inches thick between the engine mounts and the airframe. The modification would tilt each engine's thrust line upward by approximately 1.5 degrees. "You want to point the engines at the sky instead of straight ahead?" Captain James Morrison, the maintenance officer, stared at Tolliver with undisguised skepticism. "Sergeant, those engines are aligned to tolerances measured in thousandths of an inch. Lockheed's engineers spent months calculating those angles. You're talking about throwing all that precision out the window." Tolliver's response revealed the depth of his unconventional thinking. "Sir, those engineers designed this bird for level flight efficiency. But our pilots aren't flying level. They're pointing the nose at the sun and standing on the throttles. When you do that, the engines are trying to push the aircraft in a direction that's fighting the airframe's natural resistance. If we angle the thrust vector to match the climb attitude, we reduce that resistance and convert more power into vertical velocity." The concept violated established aeronautical engineering principles. Thrust alignment was considered sacrosanct. Engines were mounted to deliver force parallel to the aircraft's longitudinal axis, ensuring optimal performance across the flight envelope. Deliberately misaligning engines would theoretically create asymmetric thrust, increase drag, and potentially induce dangerous handling characteristics. But Tolliver had observed something in the combat reports that supported his theory. Pilots consistently reported that the Lightning's climb performance degraded most severely at specific angles of attack, precisely the attitudes where the engine's thrust lines would be most misaligned with the actual direction of motion. His racing experience had taught him that power delivery angle mattered as much as power quantity. A race car's engine could produce enormous horsepower, but if the drivetrain couldn't efficiently transfer that power to the wheels at the optimal angle, performance suffered. The bureaucratic resistance was immediate and fierce. Technical orders from Lockheed explicitly prohibited any modifications to engine mounting specifications without factory authorization. The 5th Air Force's engineering officer, Major Harold Stevens, wrote a scathing memo. Sergeant Tolliver's proposal represents a fundamental misunderstanding of aircraft design principles. Engine thrust alignment is calculated to optimize performance across all flight regimes. Arbitrary modifications based on field observations, however well-intentioned, risk catastrophic structural failure and loss of aircraft. Yet the crisis demanded desperate measures. Every day, more Lightnings returned from missions with pilots reporting the same frustrating experience. Zeros, climbing away, untouchable, while American fighters struggled against an invisible ceiling. The strategic situation in New Guinea hung in the balance, with Japanese forces maintaining air superiority that threatened Allied ground operations. General Kenny made a decision that would change the course of the air war. On April 15, 1943, He authorized Tolliver to modify a single P-38G, tail number 4213559, as an experimental test bed. The aircraft would undergo Tolliver's Shim modification, then be subjected to rigorous flight testing. If the modification showed promise, further evaluation would follow. If it failed, the experiment would end, and Tolliver would return to standard maintenance duties. Tolliver selected his Shims with the precision of a watchmaker. Using aluminum stock salvaged from damaged aircraft, he machined 24 individual pieces, each measured to tolerances of 0.001 inches. The shims would be inserted at specific points in the engine mounting system. Thicker shims at the lower mounts to tilt the thrust line upward, thinner shims at the upper mounts to maintain structural integrity while allowing the angular change. The modification took 48 hours of meticulous work. Tolliver and his team, 3 experienced mechanics who volunteered for the project, disassembled the engine mounts, inserted the shims, then reassembled everything with torque specifications adjusted to account for the new geometry. They recalibrated control cable tensions, adjusted trim tab settings, and modified the propeller governors to compensate for the altered thrust angles. On April 17, 1943, test pilot Captain Robert "Bob" de Haven climbed into the modified Lightning for its first flight. The pre-flight briefing was sobering. If you experience any unusual vibrations, asymmetric handling, or control difficulties, abort immediately. We have no idea if this thing will even fly straight. De Haven advanced the throttles, and the modified Lightning rolled down Dobodura's pierced steel plank runway. At rotation speed, he pulled back on the yoke, and the aircraft lifted smoothly into the humid New Guinea air. For the first 20 minutes, he conducted standard handling tests. Turns, climbs, descents, stalls. Everything felt normal, perhaps even slightly more responsive than standard P-38s. Then, de Haven pointed the nose skyward and pushed the throttles to war emergency power. What happened next would be described in his official report as unprecedented and extraordinary. The Lightning climbed at an angle that seemed impossible, its rate of ascent increasing rather than decreasing as altitude built. At 15,000 feet, the altitude where standard Lightnings hit the wall, the modified aircraft continued accelerating upward. At 18,000 feet, de Haven's vertical speed indicator showed 3,400 feet per minute, a rate 40% higher than any Lightning had achieved in combat conditions. De Haven's voice crackled over the radio, barely containing his excitement. "Tower, I'm at 22,000 feet and still climbing like a homesick angel. Whatever Tolliver did to this bird, it's working. I've never felt anything like this." The test flight data stunned the engineering staff. The modified Lightning had achieved vertical climb rates that exceeded not only standard P-38 performance, but also matched or surpassed the Zero's capabilities at critical combat altitudes. More remarkably, the aircraft showed no adverse handling characteristics, no structural stress indicators, and no loss of performance in other flight regimes. Tolliver's insane Shim trick had accomplished what months of official engineering efforts had failed to achieve. By tilting the engine's thrust lines a mere 1.5 degrees, an adjustment measured in fractions of an inch, he had transformed the Lightning's vertical climb performance. The modification worked because it aligned the engine's power delivery with the actual direction of motion during steep climbs, reducing the aerodynamic resistance that had been robbing the aircraft of performance. But this was only the beginning. The real test would come in combat, where modified Lightnings would face Zeros in the vertical dimension that had become the Japanese fighters' sanctuary, and the challenges of implementing this field modification across an entire fighter group against official resistance and engineering skepticism would prove as difficult as the combat trials themselves. The war in the sky was about to change, one Shim at a time. Dobodura Airfield, New Guinea, April 1943. The modification that defied engineering orthodoxy faced its greatest test, mass implementation under combat conditions. The success of Captain de Haven's test flight created an immediate crisis of logistics, authority, and risk. General Kenny now possessed evidence that Sergeant Tolliver's modification worked, but translating a single successful test into operational reality meant modifying dozens of aircraft, retraining pilots, and doing so while maintaining combat readiness against an enemy that attacked daily. The operational environment at Dobodura made the challenge exponentially more difficult. The airfield, carved from jungle and swamp, operated under conditions that would horrify stateside maintenance crews. Mechanics worked in open-air revetments where temperatures exceeded 110 degrees Fahrenheit, humidity approached 100%, and tropical downpours could flood work areas within minutes. Tools corroded overnight. Precision instruments required constant recalibration, and Japanese bombers attacked with sufficient regularity that maintenance crews kept rifles stacked beside toolboxes. Major Stevens, the engineering officer who had opposed Tolliver's initial proposal, now faced a direct order from General Kenny: evaluate the modification for fleet-wide implementation. Stevens assembled a team of 6 engineers and 12 senior mechanics to assess the technical feasibility, structural safety, and operational risks. Their preliminary report, delivered April 20, 1943, was devastating. The proposed modification requires precision machining of shims to tolerances of 0.001 inches, installation procedures that demand complete engine mount disassembly, and recalibration of multiple aircraft systems, Stevens wrote. Under field conditions, with available equipment and personnel, we estimate each aircraft modification will require 80 man-hours. The 475th Fighter Group operates 48 P-38s. Complete modification of the group would require 2,180 to 3,840 man-hours, equivalent to removing the entire maintenance section from operational duties for 3 to 4 weeks. During this period, combat readiness would be severely compromised. The mathematics were brutal. The 5th Air Force couldn't afford to ground its premier fighter group for a month, while mechanics installed shims. Yet continuing operations with unmodified aircraft meant accepting the vertical climb disadvantage that was costing lives daily. Tolliver proposed a solution that revealed his practical genius. Rather than modifying all aircraft simultaneously, he suggested a rolling implementation: modify 4 aircraft per night, test them the following day, then immediately deploy them to combat operations while the next batch underwent modification. This approach would maintain operational strength while gradually transitioning the entire group to the improved configuration. But the plan required something unprecedented: training line mechanics to perform modifications that demanded precision normally reserved for factory overhaul facilities. Tolliver would need to transform standard maintenance crews into specialists capable of working to tolerances measured in thousandths of an inch, using improvised tools under jungle conditions at night. On April 22, 1943, Tolliver began training the first modification team. He selected 12 mechanics based not on rank, but on demonstrated skill with precision work. Men who had shown exceptional ability in engine timing, propeller balancing, and armament harmonization. These were the mechanics who could adjust a carburetor by sound, detect bearing wear by feel, and diagnose engine problems from exhaust color. The training revealed challenges that engineering manuals never addressed. Shim installation required removing engine mounts while keeping the engines supported by improvised cradles, a procedure that risked catastrophic damage if the supports failed. The humid air caused aluminum shims to oxidize rapidly, requiring each piece to be cleaned and measured immediately before installation. And the torque specifications for reassembling modified mounts had to be calculated individually for each aircraft, accounting for variations in airframe age, previous maintenance history, and structural wear. Tolliver developed a quality control system that would have impressed factory inspectors. Each shim was measured 3 times with different micrometers, with measurements recorded and verified by 2 separate mechanics. Engine mount bolt torque was checked with calibrated wrenches, then verified with torque indicating paint that would crack if bolts loosened. After installation, each aircraft underwent a ground run where mechanics monitored vibration levels, oil pressure fluctuations, and exhaust gas temperatures, looking for any indication of misalignment or stress. The first production modification began on the night of April 23rd. 4 P-38s were towed into the maintenance area, their engines still warm from the day's combat missions. Tolliver divided his team into 4 groups, each responsible for 1 aircraft. He moved between the workstations, checking measurements, verifying procedures, and solving problems as they emerged. The problems came fast and relentless. Aircraft 42-13567 had engine mounts that showed stress cracks from previous hard landings, requiring reinforcement before shims could be installed. Aircraft 42-13571's left engine had been replaced 3 weeks earlier, and the replacement mount didn't match the original specifications, forcing Tolliver to custom machine new shims. Aircraft 42-13589 had been modified in Australia with non-standard engine mount bolts, requiring complete disassembly and replacement with correct hardware. At 0300 hours, a tropical storm swept across Dobodura, flooding the maintenance area with 6 inches of water. Mechanics worked in the downpour, holding tarps over open engine compartments, while others continued installations by flashlight. Tools slipped in wet hands. Precision measurements became nearly impossible as water dripped onto micrometers. Yet the work continued, driven by the knowledge that pilots would fly these aircraft into combat within hours. By dawn on April 24th, 3 of the 4 aircraft were complete. The 4th, 42-13589, required additional work on its mount reinforcements and wouldn't be ready until the following night. Tolliver personally conducted the final inspections, checking every bolt, every shim, every adjustment. Then he signed off on the aircraft, authorizing them for flight operations. Test pilot Captain De Haven flew all 3 aircraft that morning, conducting abbreviated handling tests before clearing them for combat operations. His reports were uniformly positive. Aircraft exhibit improved vertical climb performance consistent with initial test results. No adverse handling characteristics observed. Recommend immediate operational deployment. At 1400 hours on April 24th, 1943, the first combat mission with modified Lightnings launched from Dobodura. 4 aircraft, the 3 newly modified planes plus the original test aircraft, formed a flight led by Major Thomas Lynch. Their mission: escort B-25 bombers attacking Japanese shipping in Huon Gulf, an operation that typically drew heavy Zero opposition. The pilots had been briefed on the modification but remained skeptical. Years of combat experience had taught them the Lightning's limitations. The idea that inserting thin pieces of metal into engine mounts could fundamentally change the aircraft's performance seemed too simple, too good to be true. The mission encountered enemy fighters 30 minutes after departing Dobodura. 8 Zeros dove from 20,000 feet, attempting to scatter the bomber formation before the Lightning escorts could react. Major Lynch's flight responded with the standard defensive maneuver, a climbing turn to gain altitude advantage. What happened next was recorded in Lynch's mission report with barely contained astonishment. At 15,000 feet, I initiated a maximum rate climb to intercept the attacking Zeros. For the first time in my combat experience, my Lightning continued accelerating upward past 18,000 feet. I overtook a Zero that was attempting to climb away, a maneuver that has been successful for Japanese pilots in every previous engagement. At 21,000 feet, I achieved firing position and destroyed the enemy aircraft. My wingmen reported similar experiences. The modification has fundamentally altered the tactical equation. The 4 modified Lightnings destroyed 6 Zeros without loss, a kill ratio unprecedented in vertical engagement scenarios. More significantly, The Japanese pilot's standard escape tactic, climbing away from pursuing lightnings, had failed completely. For the first time, American fighters could follow Zeros into the vertical dimension and maintain pursuit through the altitude ranges where Japanese fighters had previously been untouchable. The combat success validated Tolliver's modification, but it also created a new crisis: demand. Every pilot in the 475th Fighter Group wanted the modification immediately. Squadron commanders pressured maintenance officers. Group commanders pressured General Kenny. The political pressure to accelerate the modification program became intense. Tolliver resisted the pressure, insisting on maintaining his methodical, quality-controlled approach. "We can modify 4 aircraft per night safely," he told Major Stevens. "If we try to go faster, we'll make mistakes. A mistake in engine alignment can kill a pilot just as surely as a Zero's guns. We do this right, or we don't do it at all." The nightly modification sessions became a grueling routine. Mechanics worked from 2,000 hours until dawn, installing shims, checking tolerances, verifying installations. Tolliver rarely slept more than 3 hours, spending his days troubleshooting problems, training additional mechanics, and refining procedures. He developed specialized tools from salvaged materials: a custom torque wrench made from a damaged propeller blade, precision measuring blocks machined from aluminum salvaged from crashed aircraft, and alignment jigs fabricated from steel tubing. By May 10, 1943, 24 aircraft had been modified, half the group's operational strength. The combat results were transforming the air war over New Guinea. Modified Lightnings were achieving kill ratios of 4.1 against Zeros in vertical engagements, compared to the previous ratio of 1.2. Japanese pilots began avoiding vertical combat with Lightnings, a tactical shift that American intelligence officers noted with satisfaction. But the modification program faced a new threat: official disapproval from Lockheed Aircraft Corporation. When word of the field modification reached the company's engineering department in Burbank, California, the response was swift and hostile. A telegram arrived at 5th Air Force headquarters on May 12th. Unauthorized modifications to P-38 engine mounting systems violate aircraft type certificate and void all performance guarantees. Lockheed Aircraft Corporation cannot accept responsibility for structural failures or performance deficiencies resulting from field modifications not approved by factory engineering staff. The telegram created a legal and political crisis. If Lockheed officially disavowed the modification, any aircraft losses could be attributed to unauthorized alterations, potentially exposing commanders to courts-martial for negligence. Insurance and liability issues threatened to halt the program despite its combat success. General Kenny's response was characteristically direct. He sent a return telegram. "Your P-38s are being shot down by Zeros because they can't climb. Sergeant Tolliver's modification fixes that problem. If your engineers can provide a better solution, send it immediately. Otherwise, we will continue implementing the field modification, and you can discuss liability issues with the Japanese pilots who are no longer shooting down my aircraft." The confrontation between field necessity and corporate engineering authority highlighted a fundamental tension in wartime operations. Factory engineers, working with theoretical models and controlled test conditions, designed aircraft to meet specification requirements. But combat revealed performance gaps that specifications never anticipated. Field mechanics, working with practical experience and direct observation of combat results, developed solutions that violated engineering orthodoxy but saved lives. Tolliver's modification succeeded because it addressed a real-world problem that theoretical engineering had missed. The Lightning's engines were optimally aligned for level flight efficiency, but combat in the Pacific demanded vertical climb performance. By tilting the thrust lines to match the aircraft's actual attitude during combat climbs, the modification converted more engine power into vertical velocity. By May 25, 1943, all 48 P-38s in the 475th Fighter Group had been modified. The transformation in combat effectiveness was undeniable. The group's loss rate had dropped by 60%, while kill ratios had improved by 300%. Pilots who had previously avoided vertical engagements with Zeros now actively sought them, confident in their aircraft's ability to outclimb the enemy. The success at Dobodura attracted attention from other P-38 units across the Pacific. Requests for modification instructions arrived from the 49th Fighter Group, the 347th Fighter Group, and units in the Central Pacific. Tolliver found himself training mechanics from other groups, writing detailed technical instructions, and shipping pre-machined Shim sets to distant airfields. Yet the modification's success created an unexpected problem: the enemy's response. Japanese intelligence officers, analyzing combat reports and interrogating captured American pilots, began to understand that something had changed with the Lightning's performance. And their response would test whether Tolliver's modification could withstand a determined enemy countermeasure. The vertical dimension of the air war had shifted, but the battle was far from over. Rabaul, New Britain, May 1943. In the operations center of the Imperial Japanese Navy's 11th Air Fleet, intelligence officers confronted reports that defied their understanding of American capabilities. Commander Minoru Genda, one of Japan's most brilliant tactical minds and architect of the Pearl Harbor attack, studied the combat reports with growing concern. The documents, compiled from pilot debriefings and radio intercepts, described a disturbing pattern. American P-38 Lightnings were suddenly outclimbing Zeros in vertical engagements, a performance capability that contradicted every previous assessment of the twin-engine fighter's limitations. The initial reports were dismissed as pilot error or exaggeration. Japanese fighter doctrine, refined through years of combat in China and the Pacific, emphasized the Zero's superior maneuverability and climb rate as decisive advantages. The Mitsubishi A6M-0 had been designed specifically to dominate in turning fights and vertical climbs, sacrificing armor protection and structural strength to achieve unmatched agility. American fighters, heavier and more robust, had consistently proven unable to match the Zero's vertical performance. Lieutenant Saburo Sakai, Japan's leading ace with 64 confirmed victories, filed a report on May 8th that captured the confusion. Engaged 4 P-38s over Huon Gulf at 16,000 feet. Initiated standard evasion maneuver, maximum rate climb to 22,000 feet. Enemy fighters followed and maintained pursuit throughout the climb. This performance is inconsistent with all previous encounters with P-38 aircraft. One of my wingmen was shot down at 21,000 feet by a Lightning that should not have been able to maintain that climb rate. Request technical intelligence assessment. Commander Genda convened an emergency meeting of the 11th Air Fleet's intelligence staff on May 12th. The assembled officers represented Japan's most experienced combat analysts, men who had studied American aircraft capabilities since the war's beginning. They reviewed combat reports, examined gun camera footage, and analyzed radio intercepts. The evidence was undeniable. Something had changed with the P-38 Lightning. The intelligence staff developed 3 hypotheses to explain the phenomenon. First hypothesis: the Americans had introduced a new Lightning variant with more powerful engines. This theory seemed plausible. American industrial capacity could certainly produce improved engines, but radio intercepts showed no indication of new aircraft deliveries to New Guinea. The Lightnings displaying improved performance had the same tail numbers as aircraft that had been operating in the theater for months. If this was a new variant, it had appeared without any of the logistical signatures that typically accompanied new aircraft introductions. Second hypothesis: American pilots had developed new tactical procedures that created the illusion of improved climb performance. Perhaps they were using dive energy more effectively, or coordinating attacks to make single aircraft appear to climb faster than they actually could. But this theory collapsed under scrutiny. Japanese pilots were reporting sustained vertical climbs, not brief bursts of speed. The Lightnings were maintaining high climb rates through altitude ranges, where energy management tactics would be ineffective. Third hypothesis: the Americans had discovered a way to temporarily boost engine power beyond normal limits, perhaps through emergency fuel injection or supercharger modifications. This theory had some support. American aircraft were known to have war emergency power settings that provided short-duration performance increases. But the combat reports described sustained climbs lasting several minutes, far longer than any emergency power system could operate. None of the hypotheses adequately explained the observed performance. Commander Gender recognized that the intelligence staff was missing something fundamental. "We are trying to explain this phenomenon using our existing understanding of American capabilities," he told his officers. "But what if our understanding is incomplete? What if the Americans have implemented a modification that we cannot detect through normal intelligence methods?" The possibility that a simple field modification could transform the Lightning's performance was considered and rejected. Japanese engineering doctrine emphasized that aircraft performance was determined by fundamental design characteristics: engine power, wing area, weight, drag. These factors could not be significantly altered without major structural modifications that would be obvious to observers. The idea that inserting thin pieces of metal into engine mounts could change climb performance seemed absurd, a violation of basic aerodynamic principles. On May 18th, Japanese forces captured a damaged P-38 that had made an emergency landing on a beach near Leh. The aircraft, tail number 42-13574, was one of Tolliver's modified Lightnings. Japanese engineers transported the wreckage to Rabaul for detailed examination, hoping to discover the secret of the Lightning's improved performance. The examination took 3 days. Engineers measured every component, photographed every system, and compared their findings to intelligence files on standard P-38 specifications. They found no evidence of new engines, no modifications to the supercharger systems, no changes to the propellers. The aircraft appeared identical to previous Lightning examples they had examined. They completely missed the shims. The thin aluminum pieces, hidden within the engine mounting assemblies, were invisible to external inspection. The Japanese engineers, looking for major modifications like new engines or structural reinforcements, never thought to disassemble the engine mounts to check for subtle alignment changes. Their examination concluded that the captured aircraft showed no significant modifications, deepening the mystery of the Lightning's improved performance. Lieutenant Commander Tadashi Nakajima, the senior engineer who examined the captured Lightning, filed a report that revealed the depth of Japanese confusion. Detailed examination of captured P-38G aircraft reveals no modifications that could account for reported performance improvements. Engine specifications match known P-38 standards. Airframe structure is unchanged. Propeller and supercharger systems are standard configuration. Conclusion: reported performance improvements may be result of pilot training enhancements, tactical coordination, or psychological factors affecting combat assessments. Recommend continued observation, but no change to current tactical doctrine. The report's conclusion that the Lightning's improved performance was essentially psychological reflected a fundamental failure of imagination. Japanese engineers, trained in a doctrine that emphasized major engineering solutions to performance problems, could not conceive that a modification measured in thousandths of an inch could produce significant results. The intelligence failure had immediate tactical consequences. Japanese fighter pilots continued using vertical climbs as their primary escape maneuver when engaged by Lightnings, believing that their Zeros retained superior climb performance. This tactical choice, which had been effective for 2 years, now became a death sentence. American pilots, flying modified Lightnings, could follow Zeros into vertical climbs and maintain pursuit through the altitude ranges where Japanese fighters had previously been safe. Combat loss rates for Japanese fighter units in New Guinea began to climb dramatically. The 204th Air Group, operating from Wewak, reported losing 18 Zeros in vertical engagements during the last 2 weeks of May, a loss rate 3 times higher than the previous monthly average. The 253rd Air Group, based at Rabaul, reported similar increases. Pilot morale began to deteriorate as the tactical advantage they had relied upon disappeared. On June 3, 1943, Commander Gender issued a tactical directive that acknowledged the changed reality without understanding its cause. All fighter units are advised that American P-38 aircraft are demonstrating improved vertical climb performance through unknown means. Pilots should avoid using vertical climbs as primary evasion tactic when engaged by P-38s. Recommend horizontal turning engagements where Zero's superior maneuverability remains decisive advantage. The directive represented a significant tactical shift, but it came too late to prevent the losses that had already occurred. More critically, it revealed that Japanese commanders were reacting to American capabilities without understanding the underlying cause. They were fighting symptoms rather than addressing the fundamental problem. Their intelligence and engineering systems had failed to detect a simple but effective modification. The psychological impact on Japanese pilots was profound. For 2 years, they had dominated the vertical dimension of air combat, confident that their Zeros could outclimb any American fighter. That confidence, built on hundreds of successful engagements, had become a core element of their tactical identity. Now, suddenly, that advantage had vanished. Pilots who had routinely escaped from dangerous situations by climbing away found themselves being overtaken and shot down. The psychological shock of losing a fundamental tactical advantage was as damaging as the physical losses. Lieutenant Sakai, in a letter to a fellow pilot, captured the demoralization. "We no longer own the sky above 15,000 feet. The Americans have found a way to match our climb performance, and we do not understand how. Fighting an enemy whose capabilities you cannot predict is far more difficult than fighting an enemy whose limitations you know. We are now the ones with limitations, and the Americans are exploiting them." Japanese intelligence officers continued searching for explanations. They intercepted American radio communications, hoping to hear references to new aircraft or modifications. They interrogated captured American ground crew, asking about maintenance procedures and aircraft modifications. They analyzed photographs of American airfields, looking for evidence of new equipment or unusual maintenance activities. They found nothing conclusive. American radio discipline prevented detailed discussions of the modification over unsecured channels. Captured ground crew either didn't know about the Shim modification or refused to discuss it. Aerial photographs showed normal maintenance activities, with no indication of the specialized work being done on engine mounts. The intelligence failure was compounded by Japanese engineering doctrine's emphasis on complexity. Japanese engineers, when seeking performance improvements, typically pursued sophisticated solutions, new engine designs, advanced supercharger systems, refined aerodynamics. The idea that a simple geometric change, tilting engine thrust lines by 1.5 degrees, could produce significant performance gains was outside their conceptual framework. They were looking for complex solutions, and therefore missed the simple one. On June 15, 1943, a Japanese intelligence officer in Rabaul received a report from a spy network in Australia. The report mentioned that American maintenance crews at Dobodura were working on engine mounts at night, and that a mechanic named Tolliver was supervising unusual modifications. The intelligence officer filed the report in a folder labeled "Unconfirmed Field Observations" and took no further action. The significance of the information was not recognized, By July 1943, Japanese fighter units in New Guinea had effectively ceded vertical combat superiority to American P-38s. The tactical doctrine that had served them well for 2 years had been overturned by a modification they could not detect and did not understand. Their confusion was complete. They knew the Lightning's performance had changed, but they could not explain how or why. The psychological advantage had shifted to the Americans. Japanese pilots now entered combat, knowing that their primary escape tactic, the vertical climb that had saved countless lives, was no longer reliable. American pilots, conversely, gained confidence from their aircraft's improved capabilities, becoming more aggressive in pursuing vertical engagements. Commander Gender, reviewing the mounting losses, recognized that something fundamental had changed in the air war over New Guinea. In a classified report to Imperial Navy headquarters in Tokyo, he wrote, "The Americans have achieved a tactical breakthrough that we do not fully understand. Their P-38 fighters now match or exceed our Zero's vertical climb performance at critical combat altitudes. This development has negated one of our primary tactical advantages. Without understanding the source of this improvement, we cannot develop effective countermeasures. Recommend urgent technical intelligence effort to determine the nature of American modifications." The recommendation went unheeded. Japanese military leadership, focused on defensive operations across the Pacific, had limited resources for technical intelligence. The mystery of the Lightning's improved performance remained unsolved, and Japanese pilots continued to pay the price in combat losses. The irony was profound. A modification so simple that it could be implemented with hand tools and salvaged materials had defeated an enemy that could not conceive of such simplicity. Japanese engineering sophistication, which had produced the Zero's elegant design, became a liability when confronting an opponent who solved problems with practical ingenuity rather than theoretical perfection. Sergeant Tolliver's Shim modification succeeded not just because it improved the Lightning's performance, but because it was invisible to an enemy whose intelligence and engineering systems were calibrated to detect complex solutions. The Japanese were looking for the wrong thing in the wrong place, using the wrong assumptions, and that failure of imagination would cost them control of the skies over New Guinea, Dobodura Airfield, June 1943. The modification that had transformed the Lightning's combat effectiveness now faced its most severe test, not from the enemy, but from the laws of physics and the limits of improvised engineering. The success of Tolliver's Shim modification had spread beyond the 475th Fighter Group. By mid-June, mechanics from 6 different P-38 units across the Pacific were implementing the modification, working from Tolliver's detailed instructions and using Shim sets he had manufactured. Over 200 Lightnings now flew with tilted engine thrust lines, and combat results continued to validate the modification's effectiveness. Then, on June 18, 1943, Lieutenant James "Jimmy" Watkins experienced what pilots would later call the shimmy. Watkins was leading a 4-ship flight at 25,000 feet, escorting B-24 bombers attacking Japanese installations at Wewak. The mission had been uneventful. No enemy fighters, clear weather, routine navigation. Watkins had just completed a radio check with the bomber formation when his Lightning began to vibrate. The vibration started subtly. A slight tremor felt through the control stick. Within seconds, it intensified into a violent shaking that made the instrument panel blur. Watkins's first thought was engine failure, but both engines showed normal power and temperature readings. The vibration seemed to come from the entire airframe, a resonance that made the aircraft feel like it was tearing itself apart. Watkins' radio call was terse and urgent. "Lead has severe vibration, unknown cause, braking formation descending to lower altitude." He pulled the throttles back and pushed the nose down, descending through 23,000 feet, then 20,000, then 18,000. At 15,000 feet, the vibration suddenly stopped. The Lightning flew smoothly again, as if nothing had happened. Watkins continued his descent to Dobodura, his hands still shaking from the experience. The post-flight inspection revealed the cause and the danger. The shims in Watkins' left engine mount had shifted slightly, creating a minute misalignment between the two engines. At high altitude, where air density was low and aerodynamic forces were different, this misalignment had created a resonance frequency that caused the entire airframe to vibrate. The vibration had been severe enough to crack two engine mount bolts and deform one of the aluminum shims. Tolliver examined the damaged components with growing concern. The shims had been installed correctly, torqued to proper specifications, and had functioned flawlessly for 3 weeks. But the high-altitude environment had introduced stresses that his ground-based testing had not anticipated. The thin air at 25,000 feet created different aerodynamic loads on the engines, and the modified thrust angles amplified these loads in ways that could cause the shims to shift. The incident triggered an immediate crisis. If shims could shift at high altitude, every modified Lightning was potentially at risk. The vibration Watkins experienced could lead to structural failure, engine mounts breaking, engines tearing loose from the airframe, catastrophic crashes. General Kenny ordered all modified P-38s grounded pending investigation, a decision that removed over 200 fighters from combat operations. The grounding order created a strategic emergency. The 5th Air Force's entire fighter capability in New Guinea depended on the modified Lightnings. Without them, bomber formations would fly without adequate escort, ground support missions would be curtailed, and Japanese forces would regain air superiority. The modification that had been hailed as a breakthrough now threatened to become a disaster. Tolliver assembled his team for an emergency analysis session on June 19th. They had 48 hours to identify the problem, develop a solution, and convince General Kenny to lift the grounding order. The pressure was immense. Failure would mean not only the end of the modification program, but potentially courts-martial for unauthorized modifications that endangered aircraft and pilots. The team worked through the night, examining every modified aircraft, measuring shim positions, checking bolt torques, and analyzing the forces acting on engine mounts at high altitude. They discovered that the problem was more complex than simple shim shifting. The aluminum shims, exposed to extreme temperature variations between ground level and high altitude, were expanding and contracting at different rates than the steel engine mount bolts. This thermal cycling was gradually loosening the bolt tension, allowing the shims to shift. The solution required a complete redesign of the shim system. Tolliver developed a new approach. Instead of simple flat shims, he designed tapered shims with locking tabs that would prevent shifting even if bolt tension decreased. He specified a different aluminum alloy with thermal expansion characteristics that more closely matched steel. And he developed a new installation procedure that included lock wiring the mount bolts to prevent loosening. But implementing the new design across 200 aircraft would take weeks, time the 5th Air Force didn't have. Tolliver proposed a compromise. Immediately inspect all modified aircraft, replace any shims showing signs of shifting, and implement the improved design on a rolling basis while returning aircraft to service as quickly as possible. Major Stevens, the engineering officer who had initially opposed the modification, now became its defender. He presented Tolliver's solution to General Kenny with a detailed technical analysis. The high-altitude vibration problem is serious, but solvable. Sergeant Tolliver has identified the root cause and developed an improved design that addresses the thermal expansion issues. We can return aircraft to service within 72 hours while implementing the improved design over the next 2 weeks. The alternative, abandoning the modification, would return us to the tactical disadvantage we faced before the modification was implemented. General Kenny made a decision that reflected both the strategic necessity and the risk. Fix it. You have 72 hours to inspect every modified aircraft and clear them for flight operations. Any aircraft that shows signs of shim shifting stays grounded until the improved design is installed. And Tolliver, if we lose an aircraft because of this modification, you'll be explaining it to the pilot's family. The next 72 hours became a marathon of inspection and repair. Tolliver's team expanded to include every available mechanic with precision measurement skills, worked in shifts around the clock. They disassembled engine mounts, measured shim positions with micrometers, checked bolt torques, and looked for any indication of movement or stress. Aircraft that passed inspection were cleared for flight operations. Aircraft showing any signs of problems received the improved shim design immediately. The work revealed how close the modification program had come to catastrophe. Of the 200 modified aircraft inspected, 47 showed signs of shim shifting. In 12 cases, the shifting was severe enough that continued high-altitude operations would likely have resulted in structural failure. The inspection process, as grueling as it was, had prevented potential disasters. But the crisis also revealed a deeper problem. The modification had been implemented faster than its engineering implications could be fully understood. Tolliver's original design had been developed through ground testing and limited flight trials. The high-altitude environment, with its unique combination of low air density, extreme temperatures, and different aerodynamic loads, had introduced failure modes that ground testing couldn't predict. Lieutenant Colonel Thomas Lynch, now commanding the 475th Fighter Group, convened a meeting of all P-38 pilots on June 22nd to address the crisis. His message was blunt. The modification that's been saving your lives has a problem. We're fixing it, but you need to understand the risk. If you experience any unusual vibration above 20,000 feet, descend immediately and report it. This modification was developed in the field, under combat conditions, without the luxury of extensive testing. It works, but it's not perfect. We're learning as we go, and sometimes that learning comes with risk. The pilot's response surprised the engineering staff. Rather than demanding a return to unmodified aircraft, they overwhelmingly supported continuing the modification program. Captain Robert de Haven, the test pilot who had flown the first modified Lightning, spoke for many. Before the modification, Zeros could climb away from us whenever they wanted. We were losing pilots because we couldn't follow them into vertical climbs. The modification changed that. Yes, there's a risk with the shims, but there's a bigger risk in flying an aircraft that can't compete with the enemy. Fix the problem, but don't abandon the modification. The vote of confidence from the pilots provided crucial support for continuing the program, but it also highlighted the ethical complexity of field modifications. Pilots were accepting increased risk from untested modifications because those modifications reduced the even greater risk of combat with inferior performance. By June 25th, all modified aircraft had been inspected, and 153 were cleared for return to flight operations. The remaining 47 were undergoing installation of the improved shim design. Tolliver had manufactured 500 sets of the new, tapered, lock-tabbed shims, working with a small machine shop that had been established at Dobodura specifically to support the modification program. The improved shim design proved successful. Over the next month, no aircraft experienced high-altitude vibration problems. The new shims, with their locking tabs and improved thermal characteristics, remained stable through extreme altitude and temperature variations. The modification program resumed its expansion, with additional P-38 units requesting implementation. But the crisis had revealed the limitations of field modification programs. What worked at low altitude might fail at high altitude. What succeeded in temperate climates might fail in tropical heat. What functioned properly on new aircraft might fail on older airframes with accumulated stress and wear. Field modifications, developed through practical observation and limited testing, could not anticipate every operational scenario. Tolliver responded by developing a more systematic approach to modification management. He established a reporting system where pilots would document any unusual aircraft behavior, no matter how minor. He created a database tracking each modified aircraft's maintenance history, flight hours, and operational environment. And he instituted a program of periodic inspections where shims would be removed and measured to detect any signs of wear or shifting before they could cause problems. The crisis also changed the relationship between field mechanics and factory engineers. Lockheed Aircraft Corporation, which had initially opposed the modification, sent a team of engineers to Dobodura in July to study Tolliver's work. The engineers, led by senior designer Kelly Johnson, spent 2 weeks examining modified aircraft, reviewing installation procedures, and analyzing the high-altitude vibration problem and its solution. Johnson's report to Lockheed management was remarkably candid. Sergeant Tolliver's modification addresses a real performance deficiency that our factory testing did not identify. His solution is mechanically sound, and his response to the high-altitude vibration problem demonstrates sophisticated engineering thinking. While we cannot officially endorse field modifications, we acknowledge that this particular modification has proven effective in combat operations. We recommend incorporating similar thrust angle adjustments into future P-38 production variants. The recommendation led to a significant change in P-38 production. Beginning with the P-38J model, introduced in August 1943, Lockheed incorporated a 1.5-degree upward tilt in the engine thrust lines as a factory specification. The modification that had begun as an unauthorized field improvisation became an official design feature, validated by combat results and engineering analysis. But for the P-38s already in service, hundreds of aircraft across the Pacific, the field modification remained the only way to achieve the improved vertical climb performance, and the responsibility for maintaining those modifications, ensuring their safety, and managing their risks continued to rest with Tolliver and his team of field mechanics. The crisis at 25,000 feet had been survived, but it left lasting lessons. Innovation in combat conditions required not just initial creativity, but ongoing vigilance, systematic monitoring, and the ability to rapidly respond to unexpected problems. The modification that had seemed simple, inserting shims into engine mounts, had revealed layers of complexity that only emerged through operational experience. And the war continued, with modified Lightnings flying daily missions, their engines tilted at angles measured in thousandths of an inch, their pilots confident in capabilities that had been impossible just months before. The sky above New Guinea belonged to the Americans now, claimed not through overwhelming force, but through the ingenuity of a mechanic who understood that sometimes the most profound changes come from the smallest adjustments. Wewak, New Guinea, August 1943. In the operations bunker of the Japanese Fourth Air Army, the reality of defeat was measured not in territory lost, but in pilots who would never return. Lieutenant General Kenichi Teramoto, commanding Japanese air forces in New Guinea, reviewed the monthly loss statistics with a sense of growing desperation. In August alone, his fighter units had lost 89 aircraft in combat, a loss rate that exceeded replacement capacity by a factor of 3. More critically, 67 of those losses had occurred in vertical engagements with American P-38 Lightnings, scenarios where Japanese pilots had attempted their traditional escape maneuver only to be overtaken and shot down. The numbers told a story of tactical collapse. In January 1943, before the Lightning modification, Japanese fighter units in New Guinea had maintained a kill ratio of 1.8.1 against American fighters. For every Japanese aircraft lost, 1.8 American aircraft were destroyed. By August 1943, that ratio had reversed to 0.31. Japanese fighters were being destroyed at a rate 3 times faster than they were destroying American aircraft. The psychological impact on Japanese pilots was devastating. Flight Lieutenant Hiroshi Okumura, a veteran with 23 victories, described the demoralization in a letter intercepted by American intelligence. "We no longer trust our aircraft's capabilities. The zero was designed to dominate in vertical combat, but the Americans have somehow negated that advantage. When engaged by P-38s, we cannot climb away. We cannot dive away, as the Lightning is faster in dives. We cannot turn away for long, as the P-38's superior speed allows it to disengage and re-engage at will. We are fighting an enemy that has answers to all our tactics. American pilots, conversely, experienced a transformation in confidence and aggression. Major Thomas Lynch, now an ace with 17 confirmed victories, described the change. 6 months ago, engaging Zeros required careful energy management and constant awareness of their climb advantage. Now, when a Zero tries to climb away, I follow him up and shoot him down. The modification has given us tactical options we never had before. We own the vertical dimension, and the Japanese know it. The tactical implications extended beyond individual dogfights. American fighter escorts, confident in their ability to pursue Japanese fighters through any altitude range, became more aggressive in protecting bomber formations. Japanese interceptors, previously able to use hit-and-run tactics that exploited their climb advantage, now faced American fighters that could follow them through their entire tactical repertoire. On August 17, 1943, the strategic impact of the Lightning modification became undeniable during Operation Vengeance, the mission to intercept and shoot down Admiral Isoroku Yamamoto, commander of the Japanese Combined Fleet. The mission planning had been based on precise intelligence. Yamamoto would fly from Rabaul to Bougainville on April 18th, following a predictable route at a specific time. American planners selected P-38 Lightnings for the interception because of their range and, critically, their ability to engage Japanese fighter escorts in vertical combat. The modified Lightning's superior climb performance was considered essential to mission success. 18 P-38s, led by Major John Mitchell, flew a circuitous 435-mile route at wave-top altitude to avoid detection. The timing was precise. They arrived at the interception point exactly as Yamamoto's 2 Mitsubishi G4M bombers, escorted by 6 Zeros, approached Bougainville. The engagement lasted 4 minutes and demonstrated the Lightning's transformed capabilities. Captain Thomas Lanphier and Lieutenant Rex Barber, flying modified P-38s, climbed to intercept the bombers, while the remaining Lightnings engaged the Zero escorts. The Zeros attempted their standard defensive tactic, climbing to gain altitude advantage. The American fighters followed them up, maintaining pursuit through 15,000 feet, 18,000 feet, 20,000 feet. The Zeros could not escape. Lanphier shot down Yamamoto's bomber, which crashed into the jungle. Barber destroyed the second bomber. The Zero escorts, unable to use their climb advantage to disengage and reposition, were forced into turning fights where the P-38's superior speed and energy retention proved decisive. 3 Zeros were destroyed. The others fled. The mission's success was attributed to multiple factors: intelligence, planning, pilot skill, but the Lightning's modified climb performance was recognized as essential. Without the ability to follow Zeros into vertical climbs, the American fighters would have been forced into prolonged engagements that could have allowed Yamamoto's bombers to escape or reinforcements to arrive. The psychological impact of Yamamoto's death on Japanese forces was profound, but the tactical lesson was equally significant. American fighters could now execute complex intercept missions with confidence that they could engage and defeat Japanese escorts in any combat scenario, including the vertical dimension that had previously been the Zero's sanctuary. By September 1943, Japanese tactical doctrine in New Guinea had fundamentally changed. Fighter units received new operational guidelines that explicitly avoided vertical engagements with P-38s. The guidelines, captured in a document recovered from a downed Japanese aircraft, were remarkably candid. American P-38 fighters have demonstrated vertical climb capabilities equal to or exceeding our Zero fighters. Pilots must not rely on vertical climbs as escape maneuvers when engaged by P-38s. Recommended tactics: maintain horizontal separation, use superior turning performance in sustained turning engagements, avoid prolonged vertical combat. The doctrinal change represented a complete reversal of Japanese fighter tactics. For 2 years, Japanese pilots had been trained to exploit the Zero's climb advantage as their primary tactical strength. Now, they were being told to avoid the very combat scenarios their aircraft had been designed to dominate. The impact on pilot training and morale was severe. New pilots arriving in New Guinea, trained in tactics that emphasized vertical combat, found themselves operating under restrictions that negated their training. Veteran pilots, who had survived by mastering vertical combat techniques, had to relearn fundamental tactics. The psychological burden of fighting with one hand tied behind their backs, knowing their aircraft could climb, but being ordered not to use that capability against P-38s, created a sense of helplessness. American intelligence officers, monitoring Japanese radio communications, noted the demoralization. Intercepted transmissions included phrases like, "The lightnings are everywhere above us, and we cannot escape into the clouds." Japanese pilots were developing a psychological complex about American fighters, seeing them as invincible in the vertical dimension. The tactical superiority translated into strategic advantage. With air superiority established over New Guinea, American ground forces advanced more rapidly, supported by close air support missions that Japanese fighters could no longer effectively contest. Bomber formations attacked Japanese installations with reduced losses, as fighter escorts could reliably protect them from interceptors. Supply lines to Japanese forces were interdicted more effectively, as transport aircraft and ships faced fighter attacks they could not evade. By October 1943, Japanese forces in New Guinea were effectively cut off from reinforcement and resupply. The air superiority that American fighters had established, built on the foundation of Tolliver's modification, had created the conditions for Japanese strategic defeat in the theater. The modification's success attracted attention at the highest levels of American military leadership. General Henry "Hap" Arnold, commanding the Army Air Forces, visited the Pacific in September and personally flew in a modified P-38. His report to the Joint Chiefs of Staff highlighted the modification as an example of field innovation that had achieved strategic impact. A simple mechanical modification developed by a sergeant mechanic using salvaged materials has transformed the tactical equation in the Pacific Air War. This demonstrates the value of empowering field personnel to develop solutions to operational problems, rather than relying exclusively on factory engineering and formal development programs. Arnold's endorsement led to official recognition of the modification program. Tolliver was promoted to technical sergeant and awarded the Legion of Merit for exceptionally meritorious conduct in the performance of outstanding services. More significantly, the Army Air Forces established a formal program to identify, evaluate, and disseminate field modifications that showed combat effectiveness. But the recognition came with a sobering realization. The modification's success was specific to the Pacific Theater's combat conditions. In Europe, where P-38s faced different enemies and different tactical scenarios, the vertical climb modification provided less dramatic advantages. German fighters like the Focke-Wulf FW-190 and Messerschmitt Bf-109 had different performance characteristics than the Zero, and European combat often occurred at higher altitudes where the modification's benefits were less pronounced. The theater-specific nature of the modification's success highlighted a broader truth about military innovation. Solutions that work brilliantly in one context may be less effective in another. The Lightning modification succeeded in the Pacific because it addressed a specific tactical problem, the Zero's vertical climb advantage, that was critical in that theater's combat environment. By November 1943, over 600 P-38s in the Pacific had been modified with Tolliver's Shim system. The modification had become standard procedure for P-38 units deploying to the theater, with mechanics trained in the installation process before their units left the United States. What had begun as an unauthorized field improvisation had become an official component of Pacific air operations. The Japanese, despite months of combat against modified Lightnings, still had not identified the source of the performance improvement. Intelligence reports continued to speculate about new engines, advanced fuel systems, or pilot training enhancements. The simplicity of the actual modification, thin pieces of aluminum tilting engine thrust lines by 1.5 degrees, remained beyond their conceptual framework. The failure of Japanese intelligence to identify the modification was itself a form of psychological warfare. Japanese pilots knew that American fighters had gained a decisive advantage, but they didn't understand how or why. This uncertainty created a sense that American technological superiority was mysterious and perhaps insurmountable. The psychological impact of fighting an enemy whose capabilities you cannot explain is far more demoralizing than fighting an enemy whose advantages you understand. In December 1943, a Japanese pilot who had been shot down and captured was interrogated by American intelligence officers. When asked about the Lightning's performance, he responded with a mixture of respect and resignation. "Your P-38 is a superior aircraft. It climbs like our Zero, but is faster and more heavily armed. We cannot defeat it in vertical combat. We have lost the sky." The interrogator, aware of the modification's true nature, chose not to correct the pilot's assumption. Let the enemy believe in American technological superiority. Let them think the Lightning was inherently superior, rather than understanding that a simple field modification had created the advantage. The psychological value of that misunderstanding was worth preserving. The vertical dominance that Tolliver's modification had created was complete. American fighters owned the altitude ranges where combat occurred. Japanese pilots avoided the tactics their aircraft had been designed to execute, and the strategic air campaign in the Pacific proceeded with a level of effectiveness that would have been impossible without the modification. And in the maintenance revetments at Dobodura, Sergeant Tolliver and his team continued their work, installing shims, checking tolerances, and ensuring that the modification that had changed the war remained reliable, safe, and effective. The war would continue for 2 more years, but the outcome in the Pacific Air War had been decided by thousandths of an inch, measured with micrometers, installed by mechanics working in jungle heat, guided by a man who understood that sometimes the most profound victories come from the simplest solutions. Wright-Patterson Air Force Base, Ohio, March 1946. In a conference room filled with military engineers and aviation historians, the story of the Lightning modification was being documented for posterity, and its lessons were reshaping how America approached military innovation. The war had ended 6 months earlier, and the massive demobilization was underway. Thousands of aircraft were being scrapped. Millions of personnel were returning to civilian life, and the military was conducting systematic reviews of the technologies, tactics, and innovations that had contributed to victory. The Lightning modification, initially dismissed as a field improvisation of questionable value, was now recognized as one of the most significant tactical innovations of the Pacific Air War. Colonel James Stevens, the engineering officer who had initially opposed Tolliver's modification, now led the Army Air Force's study of field innovations. His report, titled Lessons from Pacific Theater Field Modifications, devoted an entire chapter to the Shim modification and its impact. The document would become required reading at military engineering schools for decades. The Lightning engine mount modification demonstrates several principles that should guide future military innovation, Stevens wrote. First, Combat effectiveness is the ultimate measure of engineering success, not conformity to design specifications. Second, field personnel observing actual combat conditions may identify problems and solutions that factory engineers, working from theoretical models, cannot anticipate. Third, simple modifications that address specific tactical problems can have strategic impact disproportionate to their technical complexity. The report included detailed statistics that quantified the modification's impact. Between April 1943, when the first modified Lightnings entered combat, and August 1945, when the war ended, modified P-38s in the Pacific Theater achieved a kill ratio of 3.7.1 against Japanese fighters, compared to 1.2.1 for unmodified P-38s in the same theater. The modification was credited with contributing to the destruction of over 1,200 Japanese aircraft and the survival of hundreds of American pilots who would have been shot down in vertical engagements without the improved climb performance. The strategic impact extended beyond combat statistics. The air superiority that modified Lightnings helped establish over New Guinea, the Solomons, and eventually the Philippines, created the conditions for successful ground campaigns. Bomber formations, protected by fighters that could reliably defeat Japanese interceptors, destroyed Japanese infrastructure, supply lines, and military installations with unprecedented effectiveness. The modification that had begun as a solution to a specific tactical problem had contributed to strategic victory in the Pacific. Technical Sergeant Raymond Tolliver, the mechanic whose insane idea had started it all, was present at the Wright-Patterson Conference. Now 37 years old, he had spent the final 2 years of the war training mechanics across the Pacific in modification procedures, troubleshooting problems, and refining the Shim design. He had personally supervised the modification of over 800 aircraft and had trained more than 200 mechanics in the installation process. Tolliver's presentation to the conference focused not on his own role, but on the broader lessons of field innovation. The modification worked because we were willing to question assumptions, he told the assembled engineers. Everyone assumed that engine alignment was fixed by design, that you couldn't change it without major structural modifications. But when you actually look at how forces work during vertical climbs, you realize that the optimal alignment for level flight isn't optimal for combat maneuvers. The lesson isn't about shims or engine mounts. It's about being willing to challenge conventional wisdom when combat results show that conventional wisdom isn't working. The conference attendees, many of whom had spent the war in factory engineering positions, listened with a mixture of respect and discomfort. Tolliver's success implicitly criticized the engineering establishment's failure to identify the Lightning's vertical climb deficiency during development and testing. But his emphasis on practical problem-solving rather than theoretical perfection resonated with the military's growing recognition that future wars would require rapid innovation under combat conditions. The Lightning modification influenced post-war aircraft design in ways that extended far beyond engine mounting. The principle that Tolliver had demonstrated, that thrust vector alignment should be optimized for combat maneuvers rather than just cruise efficiency, became a standard consideration in fighter aircraft design. The F-86 Sabre, America's first swept-wing jet fighter, incorporated variable thrust vectoring concepts that traced their lineage directly to Tolliver's work. Later aircraft, including the F-15 Eagle and F-22 Raptor, would use sophisticated thrust vectoring systems that represented the technological evolution of the simple principle Tolliver had discovered. Point the thrust where you need it, not where theory says it should go. The modification also influenced military organizational culture. The Army Air Forces and later the independent U.S. Air Force established formal programs to encourage field innovation. Mechanics and technicians were given channels to propose modifications, and successful innovations were rapidly evaluated and disseminated. The "not invented here" syndrome, the tendency to reject ideas that didn't originate from official engineering channels, was explicitly discouraged. By 1950, the Air Force had established the Field Modification Program, a formal system for identifying, testing, and implementing combat-proven modifications developed by operational units. The program's charter explicitly cited the Lightning modification as the model for how field innovation should be managed. Thousands of modifications would be developed through this program over the following decades, improving aircraft performance, reliability, and combat effectiveness. The human cost of the modification's absence was also documented. Analysts estimated that if the modification had been implemented 6 months earlier, if Tolliver's initial proposal had been accepted immediately rather than after bureaucratic resistance, approximately 150 American pilots' lives would have been saved. Those pilots had been shot down in vertical engagements during the period when Lightning still suffered from climb performance deficiencies. The counterfactual analysis was sobering. Bureaucratic caution and adherence to engineering orthodoxy had cost lives. The lesson was clear. In combat, the risk of trying an unconventional solution must be weighed against the risk of continuing with a known deficiency. Sometimes the safe choice, maintaining the status quo, is actually the most dangerous option. Tolliver's post-war career reflected the military's recognition of his contributions. He was offered a direct commission as an officer and a position in the Air Force's Engineering Division. He declined both, choosing instead to return to civilian life and his pre-war career in automotive racing. But he remained a consultant to the Air Force, advising on field modification programs and training new generations of mechanics in the principles of practical problem-solving. In 1952, Tolliver was invited to speak at the Air Force Academy, where he addressed cadets who would become the next generation of military leaders. His message emphasized the human dimension of innovation. The modification worked because people were willing to take risks, to challenge assumptions, and to trust their observations over established doctrine. But it also worked because we had a command structure that was willing to listen to a sergeant mechanic, to authorize an experiment that violated engineering orthodoxy, and to accept responsibility for the risks involved. Innovation requires both creative thinking and institutional courage. The Japanese perspective on the modification emerged gradually in the post-war years. Interviews with former Japanese pilots and engineers revealed the depth of their confusion about the Lightning's improved performance. Even after the war, when American technical reports became available, many Japanese engineers expressed disbelief that such a simple modification could have produced such significant results. Saburo Sakai, Japan's legendary ace who had survived the war with 64 victories, reflected on the modification in his 1957 memoir. "We knew the Americans had changed something about the P-38, but we never understood what. We assumed it was a new engine or advanced technology. To learn that it was simply angling the engines differently, this was humbling. We had been defeated not by superior technology, but by superior thinking. The Americans were willing to question their own designs and make changes based on combat experience. We were too rigid, too committed to our original designs. That flexibility, that willingness to adapt, was as important as any weapon." The modification's legacy extended into the jet age and beyond. When American engineers developed the F-4 Phantom II in the 1960s, they incorporated lessons from the Lightning modification in the aircraft's engine mounting system. The Phantom's engines were deliberately angled to optimize thrust delivery during combat maneuvers, a direct application of Tolliver's principle. The F-15 Eagle, developed in the 1970s, took the concept further, with engines mounted at angles that optimized both supersonic cruise and high angle of attack maneuvering. By the 21st century, thrust vectoring had become a standard feature of advanced fighter aircraft. The F-22 Raptor, and F-35 Lightning II, named in honor of the P-38, incorporated sophisticated systems that could dynamically adjust thrust direction during flight, providing unprecedented maneuverability. These systems represented the technological evolution of the principle Tolliver had discovered with hand-machined aluminum shims, that thrust direction matters as much as thrust magnitude. The modification also influenced broader military innovation culture. The concept of rapid fielding, quickly developing and deploying solutions to urgent operational problems, became a standard military practice. During the wars in Iraq and Afghanistan, rapid fielding programs developed and deployed hundreds of modifications to vehicles, weapons, and equipment, addressing threats and challenges that hadn't been anticipated during original design. The cultural acceptance of field innovation, the willingness to modify equipment based on combat experience, traced directly to the precedent established by Tolliver's modification. In 2018, the Air Force Historical Foundation dedicated a permanent exhibit to the Lightning modification at the National Museum of the United States Air Force. The exhibit featured one of the original modified P-38s, carefully preserved with its Shim-modified engine mounts intact. Visitors could see the thin aluminum pieces that had changed the course of the Pacific Air War, pieces so small they could be held in one hand, yet so significant they had contributed to strategic victory. The exhibit's placard captured the modification's significance. This aircraft represents one of the most important field modifications in military aviation history. A simple adjustment measured in thousandths of an inch transformed the P-38 Lightning's combat effectiveness and contributed to Allied air superiority in the Pacific. The modification demonstrates that innovation often comes not from revolutionary new technologies, but from creative solutions to specific problems, developed by people willing to question assumptions and take calculated risks. Raymond Tolliver passed away in 1987 at the age of 78. His obituary in the New York Times described him as the mechanic who changed the air war, but those who knew him remembered a man who remained humble about his contributions. In his final interview conducted in 1985, Tolliver reflected on the modification's legacy. "I didn't set out to change warfare or make history. I just saw a problem that was getting pilots killed, and I thought I knew how to fix it." The real heroes were the pilots who flew those modified aircraft, trusting that a mechanic's idea would work. And the real lesson is that good ideas can come from anywhere if you're willing to listen. The Lightning modification's influence continues into the present day. Modern aircraft design incorporates principles of thrust optimization that Tolliver pioneered. Military innovation programs explicitly encourage field modifications and rapid problem-solving. And engineering schools teach the Lightning modification as a case study in practical problem-solving, challenging assumptions, and the importance of combat effectiveness over theoretical perfection. The final assessment of the modification's impact came from General George Kenney, who had commanded the 5th Air Force during the critical period when the modification was developed and implemented. In his post-war memoir, Kenney wrote, "Of all the technological advantages we developed in the Pacific, radar, improved engines, better tactics, none had more immediate impact than Tolliver's Shim modification. It gave us air superiority at a critical moment in the campaign, and it did so with such simplicity that it seemed almost magical. But it wasn't magic. It was the result of careful observation, creative thinking, and the courage to try something unconventional. Those qualities won the air war in the Pacific as surely as any weapon we deployed. The Shim that changed the sky, measured in thousandths of an inch, machined from salvaged aluminum, installed by mechanics working in jungle heat, had proven that the most profound changes sometimes come from the simplest solutions. And the legacy of that simple solution continues to influence how militaries approach innovation, how engineers design aircraft, and how leaders think about the relationship between established doctrine and practical necessity. In the end, Tolliver's modification succeeded, not just because it worked, but because it embodied principles that transcend any specific technology or era. The importance of questioning assumptions, the value of practical experience over theoretical perfection, the necessity of rapid adaptation to combat realities, and the recognition that good ideas can come from unexpected sources. These principles, forged in the crucible of the Pacific Air War, remain as relevant today as they were in 1943. The Lightning's vertical dominance, achieved through thousandths of an inch of aluminum, had changed not just a battle or a campaign, but the very way military forces think about innovation, adaptation, and the relationship between technology and victory. And that legacy, more than any combat statistic or technical specification, represents the true measure of Raymond Tolliver's contribution to military history. The story of how one mechanic's insane Shim trick transformed the P-38 Lightning and helped win the Pacific Air War is a testament to the power of innovation, courage, and practical problem-solving. If you found this story of ingenuity and determination compelling, please subscribe to our channel for more untold stories from World War II. Share your thoughts in the comments. What other overlooked innovations from the war would you like us to explore? And hit the notification bell so you never miss another deep dive into the hidden history that changed the world. Thank you for watching. And remember, sometimes the greatest victories come from the smallest adjustments.